So last time we talked about three things. The first thing is the molar mass, or it called the formula mass. Okay, last time we talked about the formula mass. Formula mass, like a sodium carbonate. Okay, sodium carbonate, the formula mass or the molar mass of the sodium carbonate. So let's first talk about formula mass. Formula mass is talk about what is the mass for this formula, which means the total mass of this compound. 2 sodium plus 1 carbon and 3 oxygens. So the formula mass, you just look at what is the molar mass, what is the mass or the atomic mass for each of those elements, and then you add them together. That's it. Since we have a 2 sodium, and then that's just a sodium times 2, a plus 1 carbon. You have 1 carbon up here, and 3 oxygens. So you have oxygen and times 3. So you add the mass all together, you will figure out that formula mass. For the sodium, that's a 22.98977. That's AMU. And you times 2 AMU, that's the average atomic mass, which means it's the mass of this atom, the mass of the atom. And the plus the carbon is 12.011 AMU. And the plus oxygen, you have a 3 oxygen. Each of the oxygen is a 15.9994. You times 3. So you put that into your calculator, and the overall together is the formula mass, 22.98977 times 2 plus 12.011 plus 15.9994 times 3. And you got 105.98874. 105.98874. So that's gonna be the AMU, which means this is the formula mass of the sodium carbonate. Okay, and also we talk about another concept. It's called the molar mass. Formula mass is just to talk about is the mass of this formula. What's the mass of the formula in AMU, which means the average atomic mass. It's a small, very, very small unit. It just talk about the single, if we have the one sodium carbonate molecule, what is the mass of this molecule? Okay, so that is the formula mass. Molar mass is talking about if we have a 1 mole of the molecule, which means we have a 6.02 times 10 to the 23rd of that much molecules aggregated together. What is the mass? What is the mass? Okay, in gram. So molar mass and the formula mass actually is exactly the same number, but the only difference is unit difference. Molar mass of the sodium carbonate is just 105.98874 gram per mole, which means we have a gram per 1 mole of this molecules. If we have 1 mole of this molecule, what is the mass? And this mass is in gram. The molar mass, the slash can be rewrite like a gram divided by mole. Okay, so generally this is the unit. Gram divided by mole. That is the unit for molar mass. You can call this as a gram per mole. Gram per mole. Okay, so that's a gram per mole. Okay. All right, so we talk about, this is first concept we talked about last time, talk about what is the mass for the formula. And also, we also talk about the unit conversion. not the unit conversion, but it's a conversion between mass to the mole and the mole to the mass. So we know mass should be equal to the mole time the molar mass. Okay, so we can write this as molar mass. So mole time molar mass is equal to the mass. So if you convert mole and mass, you have to have the molar mass for the formers. Yeah, you have to know this. And if you want to convert mole to the mass to the molar mass, okay? So the mass divided by the molar mass will give us the mole. Okay, so that is the conversion between mass and mole. If you have a mass, you time mole time molar mass, you got a mass. If you have a mass divided by molar mass, you got a mole. Okay, so that is the relationship between each others. And also we talk about the conversion between mole and the molecules. Okay, molecule number, the molecule is not equal to mole. Okay, obviously, if you look at this, you know the difference. But if you're reading the questions, can you really figure out what's the difference between molecule and the moles? Okay, so when you read the question, you need to read it carefully. Okay, some of the question asking for mole, or some of the question asking for molecule. So you need to carefully understand which one is a mole, which one is a molecule. Molecule usually has a really, really big number, right? Yeah, because when we talk about molecule, we're not talking about single one molecule, two molecule. We usually talk about 10 to the 23rd or 10 to the 22nd numbers of the molecules. That's going to be a really, really big number. But usually for mole, we're not talking about that much, right? Mole is an aggregate of a certain number, which is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd of those numbers is 1 mole. If 2 of that much number is a 2 mole, right? So that's why we also has a conversion between mole and the molecule number. The conversion factor is just a 6.02 times 10 to the 23rd. So if you want to convert from mole to the molecule number or molecules, that's just the mole of the number times 6.02 times 10 to the 23rd. So you're gonna have a really, really big number for this case. But if you want to find from molecule number, then you have to know what is a mole. Oh, sorry, opposite. So if you want to find a mole, then you have to using the molecule number divided by 6.02 times 10 to the 23rd. Okay, and last time we talked about when you're divided by 6.02 times 10 to the 23rd, you have to have the parentheses to cover the whole number, the Avogadro's numbers, including the exponential part. Okay, yeah, otherwise you will have a wrong calculation in your calculator. Okay, so you have to have the parentheses over there. You have to have the parentheses. And the last time we also do the practice study guide, the worksheet for the unit conversion. And today we're going to spend a little bit more time to just review one more questions. The very important part last time we talked about, when you do such questions, you need a clear map, which means you need to know how to convert to each other. You know, mass can convert to the mole, and the mole can convert to the molecule. Okay, molecule number. So now, let's just look at the question number 3. When you read this question, you need to know where are we? What's the question gave to us? And what's the question asking for? Okay, the question asking for how many gram, you see, how many gram? Gram, that's a unit for mass. So the question is asking for mass, okay? And the question gave how many gram are there in 2.3 times 10 to the 24th atoms of the silver. The atom of silver is just the molecules, right? We talk about if 1 mole of certain something could be 1 mole could be 6.02 times 10 to the 23rd of atoms. Could be the same amount of the molecules. Could be the same amount of the ions. That really doesn't matter. But 1 mole is 6.02 times 10 to the 23rd. So generally, this is giving us the molecules numbers. Okay, it's not talking about mole. And again, this number is really big, right? 10 to the 23rd. So obviously, it's not a mole. The question it gave us is a 2.3 times 10 to the 24th. So we know the molecule number. Then you just based on the map. Then what are we gonna do? So when we read this question, so obviously, we got the molecule number. Then you have to convert that to the mole first. And then you convert the mole to the mass again. You see? So this is give you the map. And you know where are you, and you know where should we go. And then you just go that step by step. Then you will figure out what is the how to convert this. Okay, so we can just do this step by step. First, you need to find the moles. Okay, the mole should be equal to the molecule number divided by Avogadro's number. So we have a 2.3 times 10 to the 24 atoms for this molecule, and divided by Avogadro's number 6.02 times 10 to the 23rd. Okay, so in this case, you see, for the first step from molecule to the mole, you don't even have to know what kind of material it is. Okay, as long as you know the molecule number, you can directly convert that to the mole. Okay, yeah. So let's just put that into the calculator. Again, remember 6.02 times 10 to the 23rd, you're gonna have a parenthesis. So now we have 2.3 times 10 to the 24th. And by the way, you're gonna be familiar with your calculator and be familiar how to using the 10 to the x, okay, in your calculator. So this is 2.3 times 10 to the 24th divided by parenthesis 6.02 times 10 to the 23rd parenthesis equal. So now we got this number 3.8206. Okay, so 3.8206. This is in mole because the question, the Avogadro's, the number, molecule number divided by Avogadro number. So we got a mole. Okay, so this is the first step. We got a mole. Okay, yeah. And again, for this, the mole is an intermediate question, is an intermediate answer, which means this is not the final answer. So please don't round this number to 3.8. Okay, yeah. You're gonna keep it as long as possible because if you write just a 3.8, you're missing those numbers, and this is make the result not accurate. So please, okay, please do not run this number too much. Okay, okay. So now you got a mole, and then we're going to find the mass. Again, if you want to got the mole and the mass, you need to know what is the molar mass of this material. And here the material is a silver, which is Ag. And the molar mass of the silver, you can look at the periodic table. That's 107.8682. And this is in gram per mole. Okay, gram per mole. So 1 mole of the silver is 106.8682 gram. Okay, yeah. So you can see the molar mass of the silver is pretty heavy. Okay, yeah. So now you got a mole and you want to get a mass, and remember the equation. The mass is equal to mole times the molar mass. So you have the mole, you have a 3.8206 mole of silver, and you time the molar mass of the silver, 107.8682 gram per mole. You see, if you look at the unit, here is a mole, here is a gram per mole. This mole canceled. The unit is in gram. So you time that together. 3.8206 times 107.8682. You got 412.12. 412.12 gram. This is in gram, and this is a gram of silver. Okay, and again, if you look at the sig fig, the question give us just one number, is a 2. We have a 2 sig fig for this question, so that's why the answer is not a 412. Okay, suppose it's 41. Okay, 410. Okay, 410 gram. So that is the molar mass. That is a mass of 2.3 times 10 to the 24th atoms of the silver. Okay, yeah. So very, very important is looking at the map and convert the map from one to each other's. Okay, so look at see what we have, and then find what we need. Okay, so based on the map, go one by one. All right. Okay, so let's take a break, and then we will talk about something new. And by the way, so last time we do the worksheet, still some of you did not turn in the worksheet. So please come over, if you finish that, and please turn in your worksheet. So if you already have your turning the worksheet, I'm going to return that back to you, and I already gave you the grade. So you can use the worksheet as the part of the review things for the exam. And if you're having a chance to finish that, and please finish this as soon as possible. That's going to be, this is a very, very important part for this unit. Okay, so let's come back. The next part we're going to talk about the concept is called the percent composition, or yeah, percent composition. Percent composition, this topic is kind of like similar like the topic we learn in our lab. Okay, it generally is talk about the composition. So in the future, if you see the composition, it generally talk about what is the percentage of these things in the whole things. Okay, so remember last time we talked about we have a sand for our lab and we have a salt in the lab. And at the beginning, we measure the mass of the sand. We measure the mass of the salt, and then we mix them together. It becomes a mixture, and the mixture generally is just the sand plus salt. Okay, so if you want to figure out the percent composition for this, generally the percent composition for the sand percent generally is just the mass of sand divided by the total mass of the mixture. Okay, and you're gonna time 100%. This is just the meaning to what is the sand percent. Okay, which means what is the, okay, that is the percentage of the sand. Okay, so if you want to figure out the salt, you're doing the same thing. It's just using the mass of salt divided by total mass of the mixture. And your time 100%. Okay, so this is how we figure out percent composition. Okay, so if we talk about some the mixture, you want to figure out the percent composition for each of the species in the mixture. This is how you do. Certain mass of the one part of the mixture divided by total mass of the mixture. That's it. And time 100%. Okay, so generally this is how we do. And this equation is also need to be used in our lab. So when we go to the lab, when we do finish the calculation, this is the part that we're going to finish. Okay, yeah, we will talk about more on this. But today, in our concept, we're not just talking about the mixture. Here, we're talking about what if we have a compound. For example, we're going to measure, how about the sodium for a compound, sodium carbonate. Okay, so if we want to figure out what is the percent composition for the sodium carbonate, so what does that mean? That means, okay, you're gonna figure out, okay, what is the sodium percent in this compound? What is the carbon percent in this compound? And also, what is the oxygen percent in this compound? Okay, so that means the percent composition for a compound, not for the mixture. Okay, so if we talk about the percent composition for a mixture, generally talk about, okay, what is the species in this mixture and what is the mass for each, and using the mass to divide by the total mass of mixture, you got the percent composition. But for the compound, not a mixture, then the pure substance is generally doing the same thing. For the sodium percent, what you need to figure out is, okay, the sodium percent is just the mass of the sodium divided by the total mass of the sodium carbonate, and you time 100%. one more time, I need to very, very emphasize, when you do this calculation, you time 100%. I mean, generally in your calculator, there's no 100%, okay? So what do? You're just time 100 and leave out the percentage in your final answer, okay? So once you do a calculation, this calculation should be a fraction, okay, or a decimal. And you time 100, that's it, okay? And leave the percentage in your result, okay? Leave the percentage in your result. So this is how you figure out the sodium percent, okay? Well, if you want to figure out the carbon percentage, it's the same thing. Just using the mass of carbon divided by the mass of the sodium carbonate, and your time 100%. This gives you the carbon percentage. Oxygen is the same thing. That's just the oxygen percent. That's just a mass of the oxygen divided by mass of the sodium carbonate. And you time 100%. So this is give you the percentage for each of these elements in the sodium carbonate. Well, so you see, here we're talking about the mass of sodium carbonate. You may ask, how can we figure out the mass of sodium? How can we find the mass of sodium carbonate? Okay, yeah. So if we just based on the formula, we can find the theoretical mass percent. Okay, just based on the formula, we can using the molar mass as a mass of this compound. Okay, we can use the molar mass as a mass of this compound. Okay, again, we just assume we have one mole of this compound, and then you can figure out what is the mass. Okay, the percent composition generally is the same thing. Okay, so the molar mass of sodium, you know, right? The molar mass of sodium is 22.98977. This is in gram per mole. And the molar mass of carbon is 12.011 gram per mole. And the molar mass of the oxygen is 15.9994 gram per mole. Okay, so now we got the molar mass of this. And also in the previous lecture, we also figured out what is the molar mass of the sodium carbonate, right? The molar mass of the sodium carbonate, just slide this down. The molar mass of sodium carbonate is 105.98874. .87. 98874. 98874. This is in gram per mole. All right, so now we got a molar mass of each. And then let's just figure out what is the percent composition for each of this. Okay, so the first one, let's just move up here. That should be equal to the mass of sodium. Well, the point is the mass of sodium is not a molar mass of sodium. You gotta really see how many sodium in the formulas. We have 2 sodiums. We're not just has 1. So you're gonna time 2 as the total mass of sodium. Okay, so the number time 2 or time 3 or time something, that really depends on how many numbers of those elements in the formula. Okay, so now sodium has 2 sodiums. So you're gonna have a 2 and a time the molar mass of a sodium. The molar mass of sodium is 22.98977 gram per mole. So now this is giving us the total mass of the sodium, okay? And then you're going to divide by the total mass of the sodium carbonate, which is 105.98874. This is gram per mole, you see? Now, this number divided by this number, the units are all canceled, which means there's no such unit. So that is why the percent is always no unit. The only left over is a percentage, okay? So, and also you time 100%. So now let's just do the calculation. 2 times 22.98977 and divided by 105.98874. And we got 0.4338, okay? So remember, this is the number for this calculation. We haven't timed 100% yet, okay? So you're going to time 100%. To time 100% is not time 100 and divide by 100. Then that's meaningless, okay? So 100% generally is a 1, okay? So what you do is you time 100 and leave the percentage out, which means you time 100, 0.4338 times 100, you got a 43.38. And then you leave the 100 over there. So that means 0.4338 times 100%. It's just a 43.38%. Okay, so this is how you got the percentage. And this is a percentage for the sodium. Okay, this is a percent composition for sodium. Well, then you can do the same thing for the carbon. And since sodium carbonate only just one, sodium carbonate is only one carbon, you see, in this formula, that's only one carbon. So if you're talking about the mass of carbon, it's just 1 times the mass of the molar mass of the carbon, which is 12.011 gram per mole. And you divide by the total molar mass of the sodium carbonate, which is 105.98874 gram per mole, and you time 100%. Okay, now you divide by this, again, put that into your calculator. 12.011 divided by 105.98874. You got a 0.1133. Well, again, you time 100, you got 11.33. Okay, so you got 11.33, and this is in percent, and this is the carbon percentage. Okay, so that is the carbon percentage. Same thing for the oxygen. And but first of all, you see how many oxygen in this formula? We have 3, right? So you can have a 3 of the oxygen times the molar mass of the oxygen, 15.9994 gram per mole, divided by total mass of the sodium carbonate, 105.98874 gram per mole. Okay, so now you got this. Doing this again, 3 times 15.9994 divided by 105.98874, and you time 100, you got a 45.29. 45.29%. Okay, so now you got the percentage for 3 of those elements. Okay, yeah. So if we talk about what is the percent composition for sodium carbonate, what is the percent for sodium carbonate? And then your answer is the sodium percent in this composition is 43.38%. And the carbon percent is 11.33%. And the oxygen percent is 45.29%. So that is the percent composition of sodium carbonate. Okay, so that is the percent composition for the sodium carbonate. Okay, so now any questions so far? Pretty straightforward, right? Yeah. Okay, so now so far, we haven't do the calculation, but can you imagine that if we add up the percent of the sodium, add up the carbon percent and oxygen percent, so if we add up 3.38% plus 11.33% and plus 45.29%, what is this answer? That should be 100%. Yeah, that's great. Should be 100% because in this compound, we only have 3 elements over there. Okay, we only have 3 elements. So the percentage, you add them together, suppose is 100%. Okay, no more and no less. Okay, should be exactly 100%. Okay, so that means, okay, if we have for example, if we have elements, the composition. So if we have a compound XO2, if we have this compound, and we talk about oxygen percent of this compound is 27.2%. And what is X percent for this compound? What is another percentage for this mass, for the X or for this metal? Well, obviously it should be 100% minus 27.2%. Okay, that is the summary, because in this compound we only have 2 elements, either X or oxygen. If you know the oxygen percent, the other percentage should be just 100 minus that, because the sum of those percentage should be equal to 100%. Okay, so then you figure out the answer should be 100 minus 27.2. Then you got 72.8%. 72.8%. Make sense? Okay. Yeah. So this is how you figure out percent composition. All right. So go ahead to figure out. Okay. What is the? Let's just do 2. Okay. What is the percent composition for water? And what is the percent composition for the iron hydroxide? Okay, what is the percent composition? What is the percent composition for those 2 elements? Okay, for those 2 compounds, what is the percent composition? Okay, so let's just review the questions. So first of all, if you want to figure out the percent composition for each of this compound, water and iron 3 hydroxide, first of all, you need to know what is the molar mass for each of the elements, right? You can write down those molar mass of each of the elements. And also you need to know what is the molar mass for the total compound, okay? For the total compound. Here we already figured out, okay, for the water, since we have 2 hydrogen, 1 oxygen, the molar mass is 18.0153 gram per mole. The molar mass of the Fe3 hydroxide, that's going to be 106.86905 gram per mole. Okay, yeah, your number maybe is a little bit different because we're using the periodic table. So the molar mass is more or less a little bit different. That's totally fine, but the major result should be close. Okay, then you just need to set up the equation. The percent composition for water is just a hydrogen percent and oxygen percent. And obviously, you're going to divide by using the mass of the hydrogen, the total mass of hydrogen in the water, divided by the total mass of the water. The oxygen is total mass of oxygen divided by total mass of the water. Okay, so here is the setup. Since hydrogen have a 2, so you're going to time 2 in this compound, and you divide by the molar mass of the water. And oxygen, since in the former we have only 1 oxygen, so you just time 1 and divide by total molar mass of this compound. And you time 100%. And then let's figure out what is the percent composition. One 0.007795 times 2 divided by 18.0153. You got this number, you time 100, and you got 11.19. Okay, 11.19. 11.19. Okay, don't forget, this is a percentage. So you're gonna write the percent over there. So 11.19%. And that is the percentage for the hydrogen. Oxygen is doing the same thing. 15.9994 divided by 18.0153. Got this number, and you time 100. You got an 88.81. Okay, so 88.81. That's a percent. So for this percent composition for water, hydrogen is 11.19%. Oxygen is 88.81%. Okay, yeah. So your results should be similar, right? Your result should be similar. Okay, so the next one, that's a little bit complicated because we have 3 elements over here. Just using the mass of the iron divided by total molar mass of the iron hydroxide, and oxygen and hydrogen each divided by the molar mass of the iron 3 hydroxide. But then make sure oxygen has a 3. We have 3 oxygen in this formula, and we have 3 hydrogen in this formula. So you're gonna time 3 over here, time 3 in the hydrogen, but don't have to time anything for the iron, because we only have 1 iron over here. So that's why once you set up this, divided by 50.847 divided by 106.869.05, you time 100, 52.26. 52.26%. Okay, that's the percentage for iron. Oxygen 15.9994 times 3 divided by 106.86905 times 100. You got a 44.91. 44.91%. The last one, 1.00795 times 3 divided by 106.86905 times 100. You got 2.83. 2.83%. Okay, so now that is those numbers will be the percentage for each percent composition for the ion 3 hydroxide. Got the similar result? Okay, yeah. So generally, this is the percent composition. Okay, probably you already learned this before. Okay, yeah. Let's just review about the percent composition. What is the meaning of the percent composition? Okay, yeah. So are you clear? Any questions? Okay. So next part. Okay, one more concept for today, and then we're done for today. Okay. The next concept is called, we're going to try to, based on the percent composition from percent composition to empirical formula. From percent composition to empirical formula. Anyone heard the empirical formula before? Daniel, have you heard this empirical formula? Have you heard that before? Okay, yeah. Okay, so we're going to, so generally the next part is we're going to convert how to use the percent composition, which is the percent for each of this, to figure out the empirical formula. Okay, so first of all, let me tell you what is the empirical formula. Okay, so now there are two different formulas. So far, we learn one of the formula. For example, like sodium carbonate, right, or CO2. Or CO carbon monoxide, right? Or water. So this kind of molecule is normally shows in the world. And this kind of molecule is what we call the molecular molecule, a molecular formula, molecular. Molecular formula. So we are writing as MF, molecular formula. Okay, and there's another one formula is called the empirical formula. So first of all, I'm going to write down some of the example between the molecular formula and the empirical formula, and then we can summarize what is the difference between the molecular formula and the empirical formula. Okay, so first, if we're writing the sodium carbonate as a molecular formula, the empirical formula for the sodium empirical formula for the sodium carbonate will be exactly the same, still sodium carbonate. Okay, so if we write the water again as a molecular formula, the empirical formula for the water also exactly the same. But if we write sugar, C6H12O6, so this is a sugar, and they have 6 carbon, 12 hydrogen, and 6 oxygen for the whole sugar molecule. Okay, and the empirical formula will write like a CH2O. Okay, for the another compounds like a benzene, C6H6, that's a benzene. Okay, benzene. So we are going to, the empirical formula will be just a CH, okay? And if we have some other compounds like H2O2. This is called a hydrogen peroxide. Have you heard of hydrogen peroxide? Right? Actually, if you look at hydrogen peroxide, and then that's gonna be just HO as a, okay, so we're going to just write HO as an empirical formula. And if we have some C2H6, this compound is called ethene. Ethene, and the empirical formula will be just a CH3. Okay, so now I'm giving you 6 examples between the molecular formula and the empirical formula. Can you summarize what is the difference between the molecular formula and the empirical formula? It's a simplified, right? Yeah, empirical formula usually is the simplified formula for the molecular formula. But in some cases, the empirical formula could be exactly the same, just like the molecular formula, right? Because this formula, original formula cannot be simplified, then that's gonna be just exactly the same. But if this formula can be simplified, then the empirical formula will be the simplified formula. Okay, yeah. But let's see, what is the similarity between those two formulas? Okay, if you look at the ratio between each of the atoms or each of the elements, you can see, okay, for the sodium, that's just if you talk about for the first one, the sodium is a 2 versus 1 versus 3, right? That's a sodium versus carbon versus oxygen. So for the molecular formula, this guy is a 2 versus 1 versus 3, right? And if you talk about the empirical formula, there's also sodium versus carbon versus oxygen, still 2 versus 1 versus 3, right? And if you look at this one, the ratio between the molecular formula between the sugar, there's a carbon and hydrogen and oxygen, that's a 6 versus 12 versus 6. Well, if you look at the ratio, actually it's just a 1 versus 2 versus 1, right? Yeah. But here, the ratio between this formula is still same, 1 versus 2 versus 1, right? So if you look at it here carefully, you will realize the similarity between the molecular formula and the empirical formula is they are having the same ratio between the numbers of molecules, each of the elements, right? Yeah, the ratio is the same. Although it's not exactly the same number, but the ratio between the elements should be exactly the same for the molecular formula and the empirical formula. Does that make sense? Right? Yeah. So that is why. Okay. We can, based on the percent composition, to figure out the empirical formula. Okay. We can only figure out the empirical formula, but we cannot directly figure out the molecular formula because we can figure out the ratio. We cannot figure out how many numbers of those atoms in there, but we can know what is the ratio and the elements ratio in this formula, okay, from the percent composition. Okay, so carefully remember what is the difference between molecular formula and the empirical formula. Molecular formula and the empirical formula has exactly the same ratio for the elements in the compound, but not exactly the same numbers, but we do have the exactly same ratio for each of the elements. Are you clear? Okay, yeah. So this is the difference between the molecular formula and the empirical formula. So next one, we're going to talk about how to, based on the percent composition, to figure out the ratio of the empirical formula. Okay, so let me open some of the practice. Okay, so let's look at the question. Okay, so let's look at the question number 9. Okay, let's look at the question number 9. So first, this one is that we have a compound containing 6.9265% of the hydrogen and 94.0735% of oxygen, and has a molar mass. We don't have to worry about the molar mass first. So we just based on, okay, we have a hydrogen percent is that much, oxygen percent is that much. And then we're going to determine what is the empirical formula for this compound. Okay, so let's say we have the percentage for hydrogen and oxygen and try to based on the percentage of those two elements to figure out what is the empirical formula. So we have several steps. Okay, just as long as you can follow the steps, and then you should be able to solve the problem. Okay, so as long as you follow the steps, you should be able to solve the problem. So let's see. Let me just write down those numbers. We have, so generally, this compound is made only just two things, right? It's made by hydrogen and oxygen. It's made by hydrogen and oxygen. Okay, so let's see. Now we write what is the hydrogen percent and the oxygen percent. So hydrogen, we have a 5.9265%. And oxygen, we have a 94.0735%. Okay, so we have the percentage of this. Let's just do the calculation. Okay, what we do? So first, I'm going to write down the steps, or we call the path. How do we solve this kind of problem? First, once you have a percentage, first thing is you're going to convert the percentage to the mass of hydrogen and to the mass of oxygen. So this is the first step. Okay. And then you're going to convert the mass of each of this to the mole of each of the elements. Okay, you're going to convert that to the mole of each of the elements. So you're going to figure out based on the mass of hydrogen to figure out the mole of hydrogen. I'm going to write the pathway first, and then I'm going to explain why you're doing so. And then you figure out the mole of the oxygen. So this is the second step. And then since you find the moles of hydrogen and the moles of oxygen, and then you're going to determine the moles of hydrogen and the moles of oxygen, which moles of those elements are smallest mole number. Find the smallest mole number for the moles of hydrogen or the moles of oxygen. So you're going to find one of the moles, okay? And then you can, based on this, you figure out what is the ratio between carbon and hydrogen. And then you figure out what is the empirical formula for, oh, sorry, not the carbon, it's a hydrogen versus oxygen. Then you can figure out the empirical formula. Okay, so generally this is the steps. Okay, what we do. So let's just doing this one by one. Okay, let's see how can we figure out this. All right, so now you have the percentage for each of the hydrogen and the oxygen. How can we convert to the? How can we convert this to the mass of hydrogen and the mass of oxygen? Well, just to let you know, you can assume any of this the mass. Okay, so you can just assume some of the certain mass of the whole compound. You see, if we say the whole compound is like 1,000 grams, and then since the hydrogen is 5.9265% in 1,000 gram, then use 1,000 gram times the percentage, you got the mass of the hydrogen, okay? And if you're, so generally you just need to assume any of the numbers and then you can figure out the mass of this. Since this is a percentage, we can easily just assume this compound is 100 gram. So if we have 100 gram of this compound, the mass of the hydrogen, first you assume we have a 100 gram of compound. So the mass of hydrogen will be just equal to 5.9265% times 100 gram. So you will see that's a 5.9265 gram of the hydrogen, okay? So the mass of the oxygen is doing the same. This percent times 100 gram, then you got is a 94.0735 gram for the oxygen, okay? Well, you may ask, can I multiply other numbers, 1,000, 10,000, or 25.4, 33.1, 111? Sure, it really doesn't matter, okay? It really doesn't matter what kind of number you type. Eventually, the final result will be exactly the same. Okay, the ratio will always the same. So doesn't matter what's the number you type, the final result will be the same. The ratio will always the same. So that's why I'm just saying I'm going to assume that's 100 because this is the easiest way to do the calculation. Does it make sense, right? Yeah. All right. So now you just assume we have a 5.9265 gram of the hydrogen and 94.0735 gram of the oxygen. Next one is you're going to convert to the moles of hydrogen. Again, how to convert the moles of hydrogen? Mass over molar mass. Okay, mass over molar mass, you will find the mole of the hydrogen. Okay, so remember, so that is why I say we're using the conversion between mole and mass. This is a very common conversion in this unit. Okay, mass of the hydrogen divided by the molar mass of the hydrogen, then you will get the mole. Okay, remember this is the molar mass of hydrogen. It's not the two of the hydrogen because in this compound, we will try to figure out mole of hydrogen. It's not figure out moles of the H2. Okay, so this one is just divided by the molar mass of hydrogen. So now we have a 5.9265 gram of the hydrogen. You divide by molar mass of hydrogen, which is 1.00795 gram per mole of the hydrogen. So now in this case, you figure out moles of hydrogen. Oxygen is doing the same thing. You have the mass of the oxygen and you divide by the molar mass of the oxygen. Mass of oxygen is 94.0735 gram. Divided by molar mass of oxygen, which is 15.9994 gram per mole. And then you figure out the moles of hydrogen and the moles of oxygen. 5.9265 divided by 1.00795. You got a 5.879. 8798. 5.8. 5.879. 798. This is a mole of hydrogen, and the oxygen is a 94.0735 divided by 15.9994, 5.8798. 5.8798 mole. Okay, so now you got a moles of each. You got a moles of each of the things. Remember, that's gonna be mole of hydrogen, and this is a mole of the oxygen. Okay, now the next part, you got a moles of hydrogen, you got a moles of oxygen, and then the next one, you're gonna find what is the smallest mole number between the hydrogen and the oxygen. But if you look at the moles of each, the good thing is both are exactly the same. Okay, so it doesn't matter which one. Okay, so now you can just assume the first one will be the smallest mole number. Then the next one, you just need to using the mole of the hydrogen. So the ratio here, the hydrogen here is just using the mole of hydrogen, 5.8798 mole of hydrogen divided by itself, because we need to divide by the smallest mole number. So once you figure out which one is the smallest mole number, and each of this mole number gonna divide by smallest mole number. Okay, since those both are the same, so you will figure out, okay, so it doesn't matter which number you divide, you're got the exactly same thing. Okay, and the oxygen will also become 5.8798 divided by 5.8798. Okay, yeah, so now you divide by smallest mole number, then you will figure out this is 1. This is also 1. So that is why the empirical formula, the ratio between hydrogen and oxygen here is just 1/1. 1 versus 1. Since the hydrogen, you got the number is 1. Oxygen, you got a number is 1. So hydrogen versus oxygen is just 1/1. 1 versus 1. So now you got a ratio over here. This ratio is the ratio of the atoms between in the formula, 1 versus 1. So based on 1 versus 1, what is the empirical formula that you can write? It's just the hydrogen and the oxygen, right? It's just hydrogen and oxygen. So hydrogen and oxygen over here is just the empirical formula. So this is the empirical formula. That is the empirical formula, because you see H and O is talk about we have 1 hydrogen and 1 oxygen. That is the simplified the ratio between the formulas, 1 hydrogen and 1 oxygen. It's really just based on the ratio that we got. Okay, we got the ratio between hydrogen and oxygen is 1 versus 1. So the empirical formula is just HO. Okay, it's just HO. Daniel, do you have any question? Anyone has a question? Okay, yeah, obviously next time I will do some practice. Okay, yeah, I will give you some of the practice for finding the empirical formula. Okay, yeah, so let's continue talking about this next time. Okay, yeah, so let's move to the lab and to finish the lab report.